What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. And today, we are going to be dealing with a pretty interesting challenge problem that was brought to my attention by no one other than the one and only Miss Sheila Edstrom, our physics teacher extraordinaire here at school. And her and I got to talking. She was telling me about this interesting problem called an interrupted pendulum problem, and how well it relates the ideas of conservation of mechanical energy, kinetic and gravitational potential, since we just talked about potential energy, or gravitational potential energy, and it relates things back to Unit 3, circular motion, which we also need to keep in our back pocket in case we see circles. So we want to refresh our brains on those ideas too. So again, this is called the interrupted pendulum challenge problem. Let me show you what an interrupted pendulum looks like. Come on. Over here, I've got this really cool pendulum. You can see a mass right here, and it swings down this way. Maybe you can or can't see this because of the glare. I'm going to put a bigger mass on here. Maybe that will help you see this better. Let's go with the bigger mass. All right. So essentially what an interrupted pendulum is a giant mass, and as it swings down, I've put a peg in the middle of the length of this string. Not exactly in the middle, but between the mass and the fixed end. And when this happens, well, the pendulum is going to swing in an interesting way. Let's make sure this thing is tightened down before I go ahead and do this so it doesn't go flying off at me. There we go. All right. Swing you around. Here we go. Let's see what happens. So I'm going to drop this thing from exactly horizontal, from 90 degrees. And when I do, you see that the interrupted pendulum makes it around. Now, what's interesting about this is that as it does make it around, as I drop it from here, as I go to make it around, you see that slack comes into that mass. And we don't want slack in that mass. In fact, today, our challenge is going to be to figure out exactly where this peg needs to go so that this mass makes it around this loop at exactly the minimum speed. So where does this peg need to go so that there's just enough velocity to make it through the loop across the top? And really, it's not velocity here. It's more velocity up here. It's going to interrupt, come back up to this height here. Is there enough velocity up here to maintain its circular motion? And that's where we're going to see that Unit 3 review. So, I mean, right there, it makes it through the circle. There's a little slack, so maybe we're actually moving less than the minimum speed up there, but it does eventually catch itself, and the tension eventually keeps it back in that circle. So let's go ahead and think about this problem. Let's go ahead and draw this problem out. Here's what I see. If I go ahead and draw this problem out, I've got a couple different spots in this problem. Here's the mass, and that mass is fixed right here. Now that mass also has an interrupted peg right here, and eventually will reach the bottom of its swing, and then it will reach this spot in its swing, and after a little while, we'll get all the way back up to this spot. So we'll see us moving in a circle this way. So we see kind of this conservation of energy as it swings, and then it's hit by that peg, interrupted, and swings in this circle right here, round and round and round and round and round it goes. Okay, so this is a good picture of the problem. Let's label some key points. Let's label this point over here A. We can label this point down here B when the peg does interrupt. We can label halfway up C, and we can label this spot at the very peak of that circle D. Okay? So as we've done this, we're thinking, what are some things that are happening? What should my system include? What's going on here? And since we just talked about gravitational potential energy, I think it's easiest to include gravity in our system, or the Earth in our system. So let's say the system is the mass and the Earth. And let's go ahead and ask ourselves, if the mass and the Earth are both included in my system, then is there going to be an outside force that changes the work or the energy of my system? The answer is no. I mean, right here, there's a tension force, obviously, Ft, a small tension force, and there's Fg. But tension is not pointed parallel to this direction at all. In fact, it's completely perpendicular, so no. Down here, there's the force of gravity and the force of tension. They're not equal because tension is the centripetal force at this point. But again, it's moving in this direction right here. That's the speed, and tension is exactly perpendicular, so it's not going to cause a change in the energy. And at the very top, there is a force of gravity. If it moves at its minimum speed, there's actually no tension. That's why we see a little bit of slack. and this gravity is inside the system. So no, there are no outside forces causing changes in energy here. We see conservation. So let's go ahead and look, because the energy at A should be equal to the energy at B, which is equal to the energy at C, and is equal to the energy at D. There are no outside forces. These energies are all equal at all points. So this is why I can just say whatever energy is at A is the exact same value, total joules of energy at point B, at point C, and at point D. Regardless of the types of energy that are there, the value of total energy is going to be the same at all 4 points. So let's start tracking the energy. If this object is dropped from rest like we saw at point A, the only energy we see there is UG at point A. As it swings down to point B, we're going to call the bottom of this system, we're going to call this spot right here 0 meter height. We learned earlier that I can call any location near the surface of the Earth 0 and talk about the relative gravitational energy or change in gravitational energy based on that arbitrary height close to the surface of the Earth. So that's the plan, and that's what we're doing here. So we'll call that 0. At B, because it's at point 0, there is no more gravitational potential energy. There's no height from that reference point, but it is moving, and so we'll call that kinetic energy at B. At point C, it's now moved up a little higher. It's raised itself above that 0, so there's going to be some potential energy, gravitational potential energy there. It's still moving, so we're going to see kinetic energy at C, and then same at point D. There's going to be UG, gravitational potential energy at D, and it's going to be moving up there as well. Now, it's going to be moving fastest when all the energy is stored kinetically. So at point B, it's moving the fastest. And as it swings up, that kinetic energy is being split into UG, it should be UG, getting it to go higher. So it's going to slow down because it's moving upward. And as it gets to point D, it's going to be moving even slower because now I'm at an even taller height. Okay, so this is the idea here. And so what I'm asking myself, I wonder, the challenge is, I wonder where I need to place that peg so that that mass moves at its minimum speed through a circle. I've got to think here now, minimum speed through a circle, I've got to change my brain back over to circular motion. So if I think about circular motion, objects that move in a circle, let's say here is this mass moving horizontally and it gets pulled into a circle. At the very top of this motion, there needs to be a force that holds it in its path. And there's always going to be gravity acting on objects at the surface of our planet. So gravity is inward, and if it's moving at its minimum speed, there is no need for tension force. The idea of minimum speed through a loop tells me that gravity is a sufficient force to maintain that circular path. And so my centripetal force is equal to Fg when it's at the minimum speed. This is an idea we covered in Unit 3. So what I end up seeing is that I know my net force, mv squared over r is equal to the force of gravity mg, and it's this v right here that is that minimum speed. This is the minimum speed here. So if I want to go ahead and kind of break this down and figure out what is minimum speed in some variables, I would say v squared over r equals baby g, and I can then cross multiply, square root, v is equal to the square root of gr. This is what the minimum speed is equal to. The minimum speed is equal to the gravitational field strength on Earth times the radius of the circle it's moving in. This is what it is. And I'm trying to figure out what r is, but this is what the minimum speed is. Where is this object going to be moving the minimum speed? This object is going to move at the minimum speed at point D. So I'm interested in what's going on with the speed at point D. So as I come back over to energy, what I want to consider is what are 2 points in this motion that I feel I can find a lot of information out about easily. And for us, that's going to be at point A, and then obviously we need to look at point D. Okay? So let's rewrite our expression. I am curious about the potential energy at A and the potential energy at D, as well as its kinetic energy at D. These are the things I'm curious about. So, if I go ahead and start substituting in some variables, we'll call this H at A, we'll say this is mg height at D, and we'll say this is 1/2 mv at D squared. Let's start considering what are some measurements that I need to take. First things first, do I need the mass measurement? Do I need to know the mass of my pendulum? And the answer is no. Every term has mass in it. Mass will cancel out. I don't need that measurement to solve this problem. Let's drop that out. Will I need the height at point A? I probably will need the height at point A. That's something that I'll need. I'll need to know how high above the surface this thing is. What is this value right there? I'll definitely need to know that. Will I also need to know the height at point D? Yeah, I will probably need to know that. So I'm going to need to take some length measurements, length at height A, length at height D, and it looks like that's it because G is a constant. So let's go ahead and do this. Let's go ahead and look to see how do I know what the height is at A and how do I know what the height is at D. Let's go back to our setup so we can see this in person. I think sometimes seeing this visually in front of you is easier than seeing it on a whiteboard. So here we are. We're back here. If I think about this, and I'm going to call this location 0. Where the mass is now, this is 0, okay? When I raise this mass up to a 90-degree angle, the question is how high have I raised this mass? It starts here, way down here, way below the fixed point. How much higher is it from where it started? Here and here. Now, some of you geometry people are seeing this. You're saying, Mr. Gustin, all you're doing is taking it the length of the string up and moving it over here. And that's exactly what I'm doing. I don't care about this distance. Gravitational potential energy is simply an energy between the surface or the 0 point and its height. The path does not matter with gravitational potential energy. So how high have I moved this thing? I've moved it from here to here, and that height is simply the length of this string. Let's record that. The height at A is simply equal to, we're going to call this thing L for length of the string. That's what that measurement is. Come on back. Let's look at the height for point D. At point D, we called the height from 0, wrapping over. This is the height from 0 to here. I wonder what that measurement is. It's some fraction of L. I don't exactly know what fraction that is, but from here to the peg and up over here. If you are thinking about circles and circular motion, what we're thinking about is, well, this is half of the height, and this is the other half of the height. This right here is known as the radius of the circle. So my height at point D from 0 is 1 radius plus the second radius. My height at D is not exactly length, even though it's related to length. I can more accurately describe this as being equal to 2 times the radius. And why this helps so much is because over here, I know the radius of the circle matters. And over here, I know the length of the string matters. So I can actually go ahead and based on the length of my string, if I know the measurement for the length of my string, I can determine exactly how fast, exactly where that peg should be located to find the radius. Let's work through some math. Let's make a substitution or two here. G, now it's not H, let's go ahead and call this length for length of the string. Is equal to G times the height at D. We're not going to call it height at D. We're going to call it 2 times the radius. Plus 1/2 the velocity at D squared. And that velocity is the minimum velocity. That is the velocity at point D. We want that value to be the minimum value. As I start to work through this problem, what I end up getting, let's see, I can go ahead, bring G to both G terms over here, G times L minus 2GR equals 1/2 VD squared. I bring the 1/2 over. 2GL minus 4GR equals VD squared. And I can what I eventually end up with is that the velocity at D is equal to the square root of 2GL minus 4G times R. Is this messy? You betcha it's messy, but because I understand what these terms are, I feel more comfortable. Now I have two equations that are both equal to each other. I've got the minimum speed moving through this circle at the top, and I have the speed of the circle at the top using energy. Both of these are the same value, and because they're the same value, and because they're both in square roots, I can set this equal to this. So I get 2GL minus 4GR is equal to G times R. Or, rewritten, I can cross out all of these G's now because the G's are in every term. I get 2L is equal to 5R. 5 because I add the 4R over. And finally, what I end up with is that this radius, that peg, needs to be located at a length of a distance of 2/5 L. Whatever L is, 2/5 of that is where this peg needs to be located from the bottom up. Let's go check this out. Let's go test this out. We looked at this earlier. We saw this thing moving at about the minimum speed, right? It makes it through at about from vertical, horizontal. It barely makes it through, right? We can agree that that looks pretty close to its minimum speed. Let's check our answer. Without any numbers, let's check our answer. Make sure you have a calculator so you can check this out. I'm going to grab one as well. The length of this string, measured from the fixed point to the middle of my pendulum, is 55.5. 0.555 is the length. So if I take 0.555, and again, that's my length, I need 2/5. 2/5 of that length should be the radius. 2/5 of that length should match this distance right here. So 0.555 times 2/5 equals 0.222. I should see 22 centimeters, 22.2 centimeters. This distance here should be 22.2 centimeters if I actually have this in the right spot. Let's check. From the middle of mass, right up here, I get 22.5. 22.5, maybe it's too big. Maybe this isn't the minimum speed. Maybe there is a little bit of slack in here. But folks, 22.5 compared to 22.2, we are really darn close to this answer. Let's recap. Over here, we used two concepts. We used the idea that with the mass Earth system, there is no work done on the system. Energy at all points in this motion of the interrupted pendulum are equal. We then chose two spots that we thought were going to be useful for us to solve our problem. And again, the problem was where does that peg need to be located so that this mass makes it through that circle at its minimum speed. The idea of minimum speed brought us back to Unit 3, where we said if it's moving at a minimum speed, gravity is the only force acting centripetally. Therefore, the minimum speed is equal to square root GR. We came back to energy using the two locations, A and D, that this problem was discussing. We started using conservation of energy and algebra to determine that that speed at point D was exactly the square root of 2g, length of the pendulum, minus 4g times the radius of this circle. We now had two terms, minimum speed from our centripetal force, speed at point D from our energy, and if we wanted these two values to be the same, we wanted the speed at D to be the minimum speed. We set those two terms equal to each other. Setting them equal, what we determined was that the radius of this circle needed to be exactly 2/5 the length of the pendulum. We saw it, we set it up, we tested it with our eyes, we verified with our measurement, and we got pretty darn close to that minimum speed in the interrupted pendulum. If you've got questions, please drop them below as always, or ask me in class, send me an email. Until next time, see ya!